Okay, cool. Okay, so this is week 3. And from our discussion, I hope you guys see the structure of the math. So we talk about the vectors first. They're in vector space. And from vectors, we can construct a vector field. Basically, for example, if we have a R2, if we have a plane and assign each point with a vector, then it's a vector field. So vector field depends on xy. If it's R3, then it's xyz. And if it's a scalar field, then assign each point with a scalar. If it's a tensor field, then assign each point with a tensor. So for vectors, we can do some operations. For example, the dot product and also cross product for 3-dimensional vectors. This one is for 3D. This one is for any dimension. Definitely, we can do similar thing for the vector field. We can also do the dot product and the cross product. Because there's a spatial dependence in the vector field, so we can also do a differential operation. So basically, we know that when learned in calculus, the differential operation is defined like fx plus delta x minus fx, something like that. Take a limit. So we need to compare the value at different point, meaning that we need a function, like a value that depends on the spatial parameters. For the vectors, there's no such thing. We can only do the differential operation for the vector field. Okay, so for this kind of, by the way, feel free to stop me if you have questions. So for this kind of differential operation, there are several important, like there are 3 important operations. One is called gradient, acting on a scalar field. This guy will give us a vector field. And also divergence, acting on a vector field. This will give us a scalar field, and also the curl acting also on a vector field give us a vector field. So we will talk about these 3 operations one by one, and also talk about their physical meanings and the geometrical meanings. So for the gradient, by the way, there are many concepts associated with those operations. Also some theorem, for example, like Gauss's law, or also called divergence theorem. I think this one you should know something about it, since you like in like a 1B physics 1B class, like also like a Stokes theorem, and also like the concept of conservative force or non-conservative force. Things like that. Okay, let's talk about the gradient. Okay. So first, we need to know how to do the operation, how to do the gradient. If in the Cartesian coordinate, it's quite easy. It's just given by partial x, phi x, y, d, partial y, phi y, and partial d hat, right? So it's a vector, partial phi, partial y, and the partial z, partial z. In different coordinates, it may look different. For example, in the spherical coordinate, it's quite complicated. You need to look it up. I also didn't remember. Usually, I need it when I need it. I just Google it, like a del operation in different coordinates, something like that, or in spherical coordinates. Okay, so this is how we do the operation. Another one is the geometrical meaning. So imagine we have a scalar field in a three-dimensional space, x, y, z. This is a scalar field. We consider the this kind of a equation. So this equation represents a two-dimensional surface, right? Because without this constraint, you have 3 degrees freedom, x, y, z. With this constraint, this is we have a one. This equation corresponding to one constraint, meaning that it will kill 1 degrees of freedom, meaning that originally you have 3 degrees freedom. Now you kill 1, you get 2 degrees freedom. So a geometric shape that has 2 degrees of freedom is a surface, right? For example, if I have scalar field x squared plus y squared plus z squared, then if you set this guy to be a constant, this is nothing but a surface, like a sphere with some radius r. Similarly, if we have a scalar field in a two-dimensional, like a plane, this guy will stand for like a 9 or whatever. Then if you take the gradient, this guy is a vector. This vector will tell you the normal direction of those surface. I think you learned in class. Here, I just refresh your memory about this. For example, you can make up an example by yourself. But anyway, for example, I consider this guy. We know that. Let's consider this guy equal to 1. Then it's a circle, right? With a radius 1. This point is 1, 0. So let's take the gradient of this scalar field at this point, at this 1, 0 point. This is given by, so when you take this scalar field, it's given by, take the gradient, you get partial phi, partial x, partial phi, partial y at 1, 0 point. Partial phi, partial x is 2x, partial phi, partial y is 2y, which at x equal to 1, y equal to 0, which is 2, 0. 2, 0, this vector looks like this, right? 2, 0. Meaning you can say that this vector indeed is a normal vector at this point, at this 1, 0 point. Definitely, for all the points, this del phi is a normal vector because del phi you can say equal to 2x, 2y, which is proportional to xy. Xy is nothing but the r, this vector r, pointing in the radius direction. Right? Is it clear? Okay, cool. So you can say, so for example, if you want to get the tangent line at a point, then it's easy, right? Because once you know the normal direction, for example, I have this guy x naught, y naught. I want to get the tangent line at this point. Then you just need to assume the a random point on the line is given by x, y. Then we know that I call this point A, this point B, P. Then this PA vector is perpendicular to this normal vector you calculate. Then you can write it down. I assume this normal vector is nx, ny. Then you just get, sorry, this vector is given by x minus x naught, y minus y naught. The perpendicular meaning that x, the dot product is 0, right? So this guy is 0. This is the tangent line at this point. This is from the mathematical point of view. You can calculate the tangent line or tangent surface or whatever, or the normal line or whatever. So from the physical point of view, what we can get, so from the physical meaning, so when we talk about the physical meaning, we will always kind of borrow the physical example and help us to understand this kind of abstract mathematical equations, right? So when we talk about the del something, like the gradient of some scalar field, we usually think of it like a del of a potential, energy potential. Like what I said in the last discussion section. This guy will generate a force. So if a force can be written in this way, then this force is so-called the conservative force. Meaning that we can assign a energy potential to this force. For example, like the spring force, gravitational force, spring force, the potential is given by like this, right? And the what's that? Also the gravitational force, we can assign a force, sorry, a potential. And also the for example, if I have a point charge, then we can also assign a potential with the what's the name of this force? Electric force, whatever. The potential is given some proportional to 1/r, right? And also if I have a like the gravitational force between two massive objects is also proportional to 1/r, right? Remember, the force is given by like a g m1 m2 r squared, something like that. And then the potential is proportional to 1/r. So all these forces are conservative force. So the physical meaning of conservative force is like this force will conserve the energy of the system. It will not transfer the energy from the system to the environment. It will only transform like a energy from one form to another, like it's kind of energy flow from within the system. So for example, for this kind of a spring force, this force will only when this force is doing work, meaning that it will reduce the spring potential and increase the kinetic energy, right? So the energy stored within the spring is reduced, but the kinetic energy is increased, right? Similarly, for this kind of a gravitational force, when your gravitational force is doing work, meaning that it's reducing the gravitational force, sorry, gravitational potential. It's increasing the speed, meaning that the kinetic energy. However, there's one example which is non-conservative. For example, friction. Friction force. For example, if I have a force that's proportional to the velocity, there's no way to assign a scalar potential with this force. In this case, this friction force will not conserve the energy of the system. It will transfer the energy from the system to the environment and eventually becomes the heat temperature. The temperature will increase. Another way to say that this force is conservative is that the work done by this force is independent of the path. Okay, so if I have a point A and I have a point B, if I apply the force along the different paths, then the work done by this force is independent of the path we choose. Then it's a conservative force. This is also easy to prove. For example, this point from point A to point B, I have a force, and this is just a line integral, right? AB. If this force can be written in terms of this kind of gradient form, so this is nothing but minus phi BA, which is phi A minus phi B, right? So the work done by this force is equal to the potential energy reduced, the reduced potential energy. It's independent of the path. It only depends on the starting point and the end point. Okay, so what kind of force, there's a question, what kind of force that we cannot assign the given formula and why? So for example, for this force, sorry. Okay, generally speaking, it's associated with like the, if a force is curl free, meaning that the curl of this force is zero, then we can assign a potential with this force. We will see why. And for this one, there's no way to assign such a energy potential. Of course, it's easy to check. If you do this calculation, you will get a non-zero value. It's non-zero. And I mean, you can imagine if I can assign such a energy potential, then you always get some force that only depends on the position, right? But here you have a dependence on the velocity. There's no way to get a velocity dependent force from energy and potential like this. Yeah. Okay, so is it clear? Basically, if this force want to be a conservative force, the first step is like you need to be velocity independent. Okay, so for the divergence, let's talk about divergence. So first, similarly, how should we do this divergence? Or how should we do this operation? It's so straightforward. So imagine I have a B field, which is bx, by, bz in the Cartesian coordinate. Then this guy just give us partial x bx plus partial by partial like this. This is a scalar. This is a scalar field. So what you learn in 1B, like a physics 1B class, is like this, right? So the source of the electric field is the electric charge. So you can say this electric field is the vector field. It's a vector field. At each point, you can define a electro field. Sorry, like an electro vector, and this is an electro field. And if you take this divergence, you get a distribution of the electro charge. So to understand the physical meaning or the geometrical meaning, we can borrow this kind of a physical insight to help us to understand. So let's geometric or physical. This is what was very useful to borrow some physical examples to help us to understand the mathematical equations. Basically, you have a picture for this equation instead of just an abstract equation. So, okay, so we know that if we have a positive charge, it will have an electric field like this, right? If we have a negative charge, we will have an electric field like this, meaning that if I have a scalar field that can be written in this way, then this scalar field is the source or the sink of this vector field, right? So this scalar field, if the scalar field can be written in such a way, then this scalar field is the source if rho is positive, or
sorry, sir. Is there like for the previous term, is there missing a term? Like for the, I guess it should be divided by epsilon zero by the constant.
right. I just ignore that. This really doesn't matter. I mean, I'm talking
Oh,
about some general pictures.
oh, okay,
Sure.
thank you.
Yeah. Of course. I mean, in different units. For now, we use what's the name, like international some units, but in old E&M book, they use Gaussian units. Then it's kind of a 4 pi, something like that. It really doesn't matter. So here, I just give you a rough picture. Definitely, you're right. So when you work with some E&M problem, you need to be careful about the previous like prefactors, stuff like that. So okay, so then the scalar field is the source or the thing if this guy is negative. So so in reverse, if I have a vector field in some region, it looks like this, like a vectors pointing outside, then you know that this vector field definitely give us a non-zero divergence. So sometimes give me a picture of the vector field. You can tell by eye whether it's divergence free or not.
So do we require that all the vectors in the field would be tangent to the source? Would that be rho equals 0?
So okay, so you mean when your rho equals 0?
Mhm.
Okay, so when your rho equals 0, there it's just like this, right? So, or like a format loop. There's no source, there's no thing, right? By the way, for this case, for this case, you can imagine at the infinity there's a positive charge, at the infinity there's a negative charge. It's like a two parallel plane. Here you have a positive charge, on the other side you have a negative charge. Then you form this kind of straight line electric field. Okay, so you can say that this rho is the density, is the reason why there's a flux. So this is there's a relation between this density and the total flux. This is called Gauss theorem or Gauss' law, whatever. It's written in this form, like so if I choose a surface that enclose a region, the flux through this surface is given by the total density inside this surface, right? This guy is nothing but rho. Of course, if you really rigorous about the Maxwell equation is rho divided by epsilon naught, but doesn't matter. It's just like this guy is always true. This is called Gauss' theorem, right? Gauss' law. Yeah. So imagine if I denote this volume as V, then this surface is the boundary of this volume, which is partial V. And this is V. Did you see this expression in physics 1B? Yeah, I think so, right? Maybe you forgot, but you should saw this before. Yeah, because I thought, okay, if you didn't, it's okay.
Excuse me, we did something similar. Like for the left side, we did the same, but for the right, we did not like do the divergence. We did like the integral of the integral of the rho. Yeah, thank you.
Yeah. I mean, according to the Maxwell's equation, the rho is nothing but the divergence of this electric field, right? So they're kind of related. So you can say that you can write this equation as partial V and E equal to V, and I write this del as D because this is a differential operator, right? E. You can say that this equation is kind of a move this partial from the volume side to the vector field side. Actually, more abstractly speaking, you can think of this kind of volume from a vector space, like a V, partial V, stuff like that. And this kind of E is also a more general vector space. And this operation is a kind of an inner product or dot product between those two vector space. So it's like a partial V dot E equal to V dot DE. This actually is called the generalized Stokes theorem. Here I just point out there's something, there's some theorem like this, but you don't need to know. It's just, it's beyond this class. But I think it's good to know. You will say that Stokes theorem is also like this. It's also in this form. We will see later. And also like the, for example, for one-dimensional, okay, so let's imagine I have a one-dimensional integral. If I'm doing the integral like this, df, so dx, f, dx from a to b equal to, so you can say this is nothing but the f dA, right? So if you denote this region as L, then this is nothing but L df equal to, then here the value is evaluated at those two endpoints. The endpoint is the boundary of this region L, and becomes F. So you can see here similarly, if you write it another way, I have partial L F equal to L df. So you can see I just move this partial from the volume. Here volume is a 9 to the function side becomes D. So here the point is the Gauss theorem is just a generalization version of this guy. Is it clear? Basically here you convert volume integral to the integral at its boundary. So here is the volume integral. It becomes integral at its boundary. The boundary of a three-dimensional volume is a surface. Here, the volume integral, here the volume is a 9. Becomes integral at the boundary. The boundary is 2 points, so it's just a two evaluated A and B.
What are the requirements for Stokes? What do we need to be true?
Oh, okay. So you need to be simple connected. That's another thing. I will talk about it when I talk about the curl. And I will give an example. Actually, that is very important, like the assumption. Okay, so that's, let's check what else I want to say about. Yeah, that's all I want to say about the gradient, sorry, the divergence. So for the curl, okay, so how to do the curl? First thing we need to know how to do it, right? So it's defined as IJK. IJK. It's similar to a cross product. Partial X, partial Y, partial Z, AX, AY, AZ.
Sorry, if you don't mind, can you like screw up a little bit
Okay.
for the generalized Stokes theorem, if you don't mind? Yeah, thank you. Yeah, thank you. That's okay. I see.
Yeah, you can say they have the similar form, right? So the partial VE, VD. So here is also LD, partial LF, LDF. And you will see the Stokes theorem also have this form. This is the reason why it's called the generalized Stokes theorem. Okay, so this is how we do the curl. So how about the physical meaning and the geometrical meaning? We can also borrow the example from physics, meaning that we kind of attach physical meaning to a mathematical equation. So we know that there's a Maxwell equation looks like this. Of course, there are some prefactors I didn't remember, maybe some mu naught or epsilon naught I didn't remember. Basically, this equation tells us the source of the magnetic field is the current, electric current. I think this is what you learned in 1C, but it doesn't matter if you didn't learn it. So basically, if you have a wire, let's say, and there's a current through this wire, then the magnetic field looks like this. It's circulating around this wire, right? If you Google like a magnetic field due to a wire, then there must be a picture like this. You have a wire, then the magnetic field is kind of circulating, meaning that if a vector field can be written in this form, so a vector field J can be written in this form, then this vector J is actually the circulation density of the or the source of this kind of circulation of magnetic field B. Meaning that if you okay, so if you see some vector field like this, like kind of a circulating, then there must be a circulating source inside this region, right? Meaning that if you take, I call this vector as B, then I know that this guy must be non-zero. If this is zero, then there's no source for such circulation. So this is the physical intuition for this equation. So basically now if you give me a vector field on a two-dimensional plane or whatever, you can say by eye, like roughly speaking, you know, there in this region, there should be some curl non-zero curl. For example, if I give you some vector fields like here and something like this, or you should roughly, you should be able to determine, like in this region, the curl must be non-zero. In this region, the del must be non-zero. In this region, both are zero if they are kind of constant, right? Something like that. Also, the so-called Stokes theorem is like this. So if I have a vector field, let's say B, imagine it's a two-dimensional. It can be 3D, but let's say, let's imagine it's a two-dimensional vector B, and this guy is nothing, but you are calculating the circulation around this loop, right? This guy equal to, I call this omega, this omega dot ds, or yeah, ds. ds is dx dy, and the direction is the normal direction of this region. So remember, this guy is the circulation density, and this guy calculates the total circulation. So it tells you the total circulation unknown sum loop equal to the total circulation density within that loop. So for example, if I have a wire, I have a current, and you have some circulation magnetic field, then you do this integral, you should get something proportional to your current. Because this current is the source of this circulation. Because there's a current, then you have such a circulating vector field. Is it clear? Okay, so the circulation, why there's a question, why is its circulation density? Here is because according to this kind of intuition, like the if I have a wire, then it will create a circulating magnetic field, meaning that because we have such a current, then we have such a circulating current magnetic field. So you can regard this kind of current as a source of this circulation. Just like what we have before, we have an electro charge, then we have such a electro field that's going outwards, meaning that a non-zero flux. So you can regard this rho. Okay, so that's the one-to-one correspondence. So in the Gauss's norm, the rho is the charge density, and the electron field. And this charge density will introduce non-zero flux, right? If you choose a surface that encloses the charge, then the flux through that surface is non-zero. Now you have a electro current. That's electro current. We know that this current will introduce this kind of circulation. So this guy will give us a non-zero circulation. So similar to here, what we call this rho as charge density, we call this J as like a circulation density. And also the total flux, remember the total flux equal to the total charge inside that surface, right? Similarly, the total circulation equal to the total circulation density in that loop. So you can see there's a one-to-one correspondence. And of course, you can write this current as del cross B. This rho can be written as del dot E. So this is known as Gauss's law. This is known as Stokes' theorem. By the way, this loop can be written as the boundary of this region omega. Then you can say this is omega, this is dB. This is partial omega, this is B. Again, you have such a equation. Yeah, any question?
Can you just scroll up a little bit, please?
Okay,
That's perfect right there. Yeah, thank you.
okay, sure. So so the message I want to convey here is the even though we call them different theorem, like Stokes theorem and Gauss's law, whatever, they actually like both physically and mathematically speaking, they're actually the same. You can see this kind of a correspondence here and this kind of mathematical structure here. Yeah.
So divergence indicates tendency for an object that reacts to that field to radially move away, not just move away in any direction. Because straight lines don't do anything.
Yeah, I mean, this kind of straight line like this.
Right. So
yeah.
when we say divergence, it's a tendency to diverge in all directions, not just one.
Right. Okay, so this is Gauss's law and Stokes theorem. And for this kind of a Stokes theorem, by the way, there is a relation says like if force is conservative, then it's curl-free, right? You can prove this easily with this Stokes theorem. For example, I have a point A, I have a point B. Now I have two paths, path 1 and path 2. The work done along this path is given by F dot R along the path 1, and the work done along this path is given by this. So the difference between, so we want to prove that this guy equal to this guy, or this guy minus this guy equal to 0 if the curl is free, right? This is what we want to prove. And to prove that it's easy, it's just like this guy, 1 dot R minus 2. And so you can combine the integral region. This is 1 minus 2, right? So 1 minus 2, minus sign meaning that we just need to reverse the direction of the integral. So originally it's from, for this 2, originally it's from A to B, now it becomes B to A, right? So 1 minus 2 becomes a loop. So it's a loop, I denote as L. So it's L. We know that once you have a loop, you can apply the Stokes theorem, which is just the, I denote the region inside the loop as omega, then omega del f dx dy, and the normal vector, or ds. So we can say that if the curl is free, this guy is 0, meaning that the work done along the path 1 equal to the work done along the path 2. Yeah. Yeah, I think the time is up. So feel free to go. And this is also what I prepared for today. Actually, there one more example that where this kind of a Stokes theorem breaks down. That is because inside this region, there is a singular point. Then this kind of theorem breaks down. So this Stokes theorem only true for simple connected regions. I will talk about this in next discussion. Anyway, so yeah, if you have question, you can stay, and otherwise you are free to go.
Can't we remove finite singularities like that? Can we get around those?
Actually, no. I mean, what do you mean by remove? For example, actually, the example I want to talk about is this. this one. For this force, you can calculate the divergence. Sorry, the curl of this force is 0. So this is a plus sign. But you can see there is a singular point at the orange.
Mhm.
Right? When x, y goes to 0, this force becomes infinity or something like that. So meaning that also if you draw this force, it actually looks like this. You know that it must be non-zero. So this guy should be non-zero. But if you do the calculation directly, you get 0. If you do this kind of I, J, K, and the partial x, partial y, partial z, f, x, f, y, f, z. Here, f, z is 0. Yeah. It's a 2-dimensional vector, so 0. The third component is 0. If you do this calculation directly, you will get this one. But according to our intuition before, you should get non-zero. This is because there's a delta function at the orange at the singular point. This guy should be delta x, delta y, something like this. So yeah, but that is not captured in this calculation.
Gotcha.
So if you do this kind of calculation naively, you will get 0. So there's no way to capture this singularity by doing direct calculation.
That's because it violates the assumptions going into it.
Exactly. Yeah, you have to fix it by hand. Like you have to put this delta function by hand to make the Stokes theorem works. Anyway, that's we can talk about that next time. Okay.
Yeah, I was curious about so curl ends up being that implies conservative fields.
Oh, sorry, I just lost my connection. Can you say it again?
Yeah, del cross f equals 0 implies conservative fields. So, and I was just thinking about so like magnetic fields create perpendicular vector fields to your current, to whatever force you have. So the current, like J, the current density itself, creating the magnetic field, creates perpendicular spirals around it, right?
Right.
So conservative fields require that that does not exist. And if that does not, is that a necessary and sufficient condition? If that does not exist, we have a conservative field. Are we saying that?
Wait. So can you say it again? What's your question?
Yeah. So del cross B equals J creates circular perpendicular vector fields.
Right, like this, right?
So are we saying that if del cross F equals 0, that does not exist and that is necessary and sufficient? What I'm saying is it an equivalent statement that your field is conservative to say that it has no perpendicular vector forces?
Okay, so of course, if you are talking about the magnetic force, it's not true because the magnetic force is not along the direction of the magnetic field, right?
But I'm saying just in general case, right? So that's not conservative.
Yeah, this is not this B. If you regard this B as a force, this is not conservative.
Right. So are we saying therefore that any conservative force has no perpendicular components of its vector field, of the vector field that it's creating, right? Like del cross F equals 0 implies you can have straight lines, but you can't have anything perpendicular to it. So I'm just trying to understand if it's an equivalent statement to say the absence of the perpendicular vectors themselves implies that it must be conservative.
Wait, so this current is not let me stop Stop recording.